Hello and welcome to Aerospace Technology International's virtual roundtable on the use of imaging in NDT. My name is Ben Sampson and I am the editor of Aerospace Technology magazine. Joining us today on our expert panel is Brett Muehlhauser from North Star Imaging and Rahul Alreja from VJ Technologies. First of all, thank you all for attending, and I'll just quickly run through the format for today. So for the first half of an hour or so, we'll be discussing all things related to digital radiography and computed tomography. These NDT imaging techniques are increasingly being used for the inspection and analysis of aerospace parts and materials during things like R&D, qualification, certification, and manufacturing. So during that first half an hour, I'd like to invite you all to submit any questions you have for the panel. Then during the second half, we'll pick the best questions and put them to the panel. So I'll just introduce our experts today. Rahul is the Director of Global Sales and Marketing for VJ Technologies, a leading global provider of X-ray inspection solutions for quality control in a wide range of industries throughout the world. Rahul and his team at VJT are involved with bringing advanced technology, robotics, automation, and computer machine learning to a variety of industries, specifically targeting quality control and product flow. Authoring several technical papers, Rahul has been invited around the world to speak on next generation advances in the field of NDT, as VJT is constantly pushing the boundaries of what exists. Rahul, thanks for coming today. You just want to give a little bit of background on VJ Technologies and what you guys are up to at the moment?
Yeah, my pleasure. Good morning, good afternoon to all the attendees. Hopefully it's not good evening, but it could be for a couple of you. So VJ Technologies, we've been around for about 33 years. We have 7 locations around the world. I'm sure some of you at least know us, maybe not all. Hopefully that changes after this for good reasons. We specialize in DR, and now lately we've been pushing into CT and 99% of what we do is X-ray. And our niche in the market has always been custom kind of solutions. So we have, just like everybody else, we have certain products that people try to, that make sense for people. But our niche has always been to customize the product. So do the imaging first and then figure out product flow after that. We are one of the prime contractors here for Department of Defense, Department of Energy work. We touch a whole variety of industries, but today we're here to talk about aerospace. So be happy to share more if anybody asks, but yeah, I don't want to take up too much time.
Great, thanks, Rahul. And Brett, we've met before and done a couple of webinars, but if you could just tell me a little bit about, first of all, I'll talk about you. I'll give you a quick bio. Brett is a Research and Development Technical Fellow at NSI, working to continue advancements in digital radiography and computed tomography technologies and applications. Brett's been with NSI for 20 years, performing R&D, applications engineering, writing DR and CT training curriculum, and teaching those courses to a global audience. He's worked in the field of digital radiography for over 30 years. Brett's also worked in the aerospace industry for 15 years, performing product development, failure analysis, and product evaluations. Brett is an ASNT and NAS 410 level 3. Brett, what's NSI up to at the moment? Tell us a little bit about the company, please.
Well, thanks, Ben. Yeah, and welcome everybody. Hopefully, as Rahul said, it's not too late there. So a little bit background on North Star Imaging. We've been in business going on 35 years now. We're a ITW-owned company, so Illinois Tool Works. So in this industry, some of you are familiar with our sister companies, Magnaflux, Bueller, Instron, etc. Or in the fabrication industry, Lincoln and Hobart Welders, etc. But we're a leader in the industry, world leader for CT and digital X-ray systems. We fabricate them right here in Rogers, Minnesota, and we've got 6 different facilities worldwide. All of the facilities also have labs where we're producing inspection services as well as application studies for our customers. So I'm blessed in my career that I get to look at it just about everything in X-ray imaging that doesn't have a pulse. So everything from medical devices all the way to rockets and pretty much everything in between, dealing with microelectronics, etc. So it's a lot of fun, a lot of cool stuff that we get to work with, and it's products that are impacting humanity versus making paper clips or something. So it's pretty cool.
Great, thanks, Brett. Cheers. So for the next 30 minutes, we're going to cover as much as we can. It's quite a broad brief. Everyone should have seen the registration splash page, so should know what to expect. But we're going to cover some of the new technologies that are coming up in NDT imaging, things like AI and robotics and automation, high energy machines, additive manufacturing. We're going to cover standards and best practices, and we're going to talk about how and why people are using digital imaging technologies in NDT. So I think we'll start there with you, Rahul, if you don't mind. I mean, what would you say is the most common problem or challenge that your customers encounter when they're using digital imaging for NDT?
That's a good question. So, I think there's two camps to it. There's the people that are already using digital imaging, and then there's the people that are looking at getting into digital imaging. I'll focus on the people that are using digital imaging initially. They common concerns sometimes are, there's too many buttons to make this work, or the image appears a little bit too dark, and it's more a function of the digital imaging gives them so many possibilities and gives them so many different things that they can do with the images that it becomes a little bit overwhelming sometimes for people to be able to use them. So the challenge that we have as manufacturers and as developers of this is, how do we kind of view the user journey as they look at digital imaging and try to make it as easy for them as possible? A lot of what, because there are so many different analytical tools that are out there, the window leveling that you can do, the filtering you can do on images, etc. A lot of people are saying, oh, you're manipulating images or you're manipulating data. We're actually not. We're just bringing out what's in the imaging, and part of it is just educating people on how we are doing that. So none of what we do is, magic that we adding to images. It's more about how we're using the data that's there and presenting it better so that humans can actually see it. All these digital detectors that we use, they're 16-bit. I mean, 65,000 levels of gray, but the human eye can only see, 40, 50, 60, depending on how good your eyes are. So the idea is, how do you take those 65,000 levels of gray and you shrink it down to 60 so that you can actually evaluate it? And that's where image processing comes in, and that's where all those tools come in. And I'd say the biggest challenge is just educating users on what these tools do, how to use them appropriately, when to use them, and then be able to use them to supplement their own kind of knowledge base when they're looking at, NADCAP compliance or compliance with any of their other standards that are out there, and how to use these tools not as a replacement but as a supplement to what they're doing.
Okay, so in no ways it's not a shortcut to anything. There's no quick, there's no quick.
There's no magic button that you can press and say, "Do it all for me."
No.
We're working on it, but it's not quite there yet.
Brett, do NSI have a magic button yet? Or?
No, I wish we did. So that one, as well as the defy physics button, would be helpful. So, yeah. Really good points, Rahul. I think some of the difficulties are overcoming the mindsets of film radiography for those people that are already doing film, and getting them also used to, geometric magnification, putting the part closer to an X-ray tube, some of those type of things, smaller field of views. Using geometric magnification, you might be looking at 1 or 2 parts versus 3, 4 parts at a time, or maybe even a specific view at a time. And so getting used to that, where people are now capturing an image of, let's say, a single part versus 3, 4 parts, and then interpreting 1 part at a time, but doing it very rapidly. The other part of that equation, if you look at the people that weren't doing film, and especially the young people coming up now, where you got 4-year-olds with an iPad or a dad's phone or whatever, so they're used to electronics. Man, has that made our job so much easier when it comes to operating software. And some of them are kind of like, just get out of my way, and they dive in. But to Rahul's point is, there's a lot that you can do with the image to fool yourself also in, let's say, part's good if I don't have adequate contrast sensitivity, or it's bad because I'm manipulating it so aggressively that I'm creating artifacts that look like it might be defects. So the industry standards are pretty well established already to help us rein that in. But that's I'd say the main two things is just overcoming some of those film mindsets, and then putting controls on it so that people don't overdo it with software. Okay. And we take the same approach as he mentioned, where focusing on making things almost like a wizard, where it's very simple for the average person to jump into it, but you've got kind of like a Photoshop background. If you want to dive into the depths of the software, you can still do that.
So Brett, what would you say is the kind of biggest win for people? When they first start doing X-ray, 2D, or even CT, 3D computed tomography. I mean, when they come to you, say, "It's great, now I can do this." What's the most common thing you hear?
Yeah, so I think overall, it allows us to do things much faster than what they could do with film. So the speed all the way from the acquisition to the interpretation can be much quicker. And even if one is longer than the other, the balancing of the two combined typically nets you a better overall evaluation time. But we see commonly where we have just a matter of a few seconds in acquisition versus with film 30 to 60 seconds. And then the interpretation, because you can enhance the image with contrast enhancement at a minimum, so that the human eye can more easily see what they need to see and get indications to pop. That makes the interpretation, number one, with a higher probability of detection, and number two, it makes it faster. So it helps drive the overall cost of the production, evaluation, inspection down. And then for people that are doing failure analysis, it drives to a root cause much quicker.
Okay, great. And what do you hear, Rahul? Is it what's the kind of most common cited benefit once you've been with a client and sold them the equipment?
Yeah, I think Brett touched upon it precisely. He kind of nailed it. Digital imaging, what we're hearing from a lot of our customers is that it makes their life faster and easier. The ability, especially for some of those borderline cases or cases where they're not sure if they're looking at a piece of film and they're holding it to a light box and they're trying to see maybe there's a crack, maybe there's not a crack. Having image enhancement protocols and being able to enhance the image and being able to get a little clearer picture of what's going on inside the part makes it much easier to kind of make that determination, especially those kind of borderline cases. I think the other part is absolutely speed. When we're able to cut down, especially if you look at from film to digital, forget just the acquisition time, but then you also have the film processing time that you're saving, where you're putting the film into the chemical baths and you're trying to dry it up and you put it on a light box and then be able to analyze it. You can do that now. It's just boom, 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 and goes. And then with the level of automation you can set up into these systems, it makes it so that you can actually be imaging on one station. You can be viewing images from another part on another station, and the whole process just goes like a chain, and it can just flow. So making life a lot easier for operators to be able to do it.
So, I mean, is digital radiography, has it completely replaced film? Is anyone still doing it? Let either of you pick that up if you want. Rahul, what do you think?
I don't think film is ever completely going to go away, despite what we want to do. There are definitely advantages to film, especially when you have very complex geometries for parts. Film can actually bend around parts. You can't bend a digital detector, at least not yet. There are, and then, especially when you're looking at, say, weld imaging or instead of big kind of part, you can just actually wrap around the film and you put a panoramic source in and you can just expose the entire weld onto one piece of film. Things like that are a little bit more challenging on the digital imaging and digital detector side. However, I think, having said that, I think DR can certainly replace about 80 or 90% of what film is doing. I think there's those 10% to 15% cases where film will be necessary. I think one of the biggest challenges, especially in the aerospace side, is actually standards and having customers approve digital imaging versus film-based imaging. It's one of our biggest things that we've been working on. the primes have you know, your Boeings and your Honeywells and all have started adopting it more and more. But there is still certainly work to be done in terms of standards adoption for digital imaging.
Okay. I mean, Brett, do you still encounter people using film, and you know, are they right to do so in certain situations, like Rahul was saying?
Yeah, he brought up a great point. To just, you know, the flexibility of film, and even in the CR world out there, there's applications where film still does a better job than CR sometimes. But especially when you can't generate more magnification and whatnot. But CR has done a good job of replacing film where you have to have flexibility. But overall, that probability of detection is going up, and the aerospace primes have really embraced the use of digital, and to the point where you know, they all have their internal standards, and they're all helping establish the ASTM standards and the ISO standards. So it's very well established right now, and CT is coming along right after it. So the aerospace primes are diving into the CT development of their standards, and we work with them aggressively. But film, you know, we kid about it. We try not to say the F word too much anymore. So we digital stuff. But overall, film will be around for decades, probably to come, at least another 10 years. In fact, I spoke with a film rep about 2-3 years ago, and their film sales were still climbing, which didn't make sense, other than the applications for digital radiography and film radiography continue to go up. So when you have things like additive manufacturing, but you need to have the flexibility of the piece of film to get inside, the quantity of evaluations using radiography just continue to rise. So some of the film manufacturers are actually selling more, which is surprising. So.
Okay. We'll talk about AM and parts and the challenges they pose in a little while, but just to kind of cover off some of the benefits and that digital radiography are giving people. I mean, are there any others that we haven't covered? We're talking about speed and effectiveness, really, aren't we? Are there any others? They let people do things in any different ways, or?
Well, I think that overall, the image quality, I can speak from experience here. I've done a lot of film in the past with aerospace, and for the last 20-some years, just focusing on digital. And when it comes to detectability, I had, for example, somebody send me a weld plate, aerospace critical component that's going into space, high pressure vessel. And they sent me a sample that they used to qualify all their level 2s and level 3s for their technique development, because they have some microporosity, 3 microporosity and a micro crack in the part. I looked at it with just a simple setup with digital radiography with a microfocus and zoomed in, and I took images of all of the porosity, which was not 3, it was 13. And I took images of the 2 cracks, not the 1, and sent it back. And the guy thought I was smoking something or whatever that I was. And what are you doing? There's only 1 crack and 3 porosity in there. So I invited him out and showed him how we could establish so much more spatial resolution. So the net of that is, it concerns some people, is that, oh, wow, do I have a legitimate quality product going out the door? Well, in this case, they've been shipping that type of product for 5-10 years. So instead of being concerned about those additional microporosity, they could actually open up their acceptance criteria to reflect the part that actually went through full qualification. Now, the crack was concerning to them, obviously, but they also had liquid penetrant mag particle that they're using for surface cracks. But I've never had a situation where if I could fit the system, the product into a microfocus system for digital radiography, I've never had a situation where I couldn't see better image quality than with film, because of the geometric magnification capabilities and digital enhancement, contrast enhancement.
Okay, good. And now we're using those technologies as the aerospace industry moves towards more additively manufactured parts. And it seems intent to do so, with composites and well, metal parts mostly. Do you know, X-ray and 3D CT? I mean, where and how are they really helping that introduction? Rahul, do you want to speak to that for a while?
Yeah, for sure. I think, you know, AM and 3D printed parts represent some of the most, you know, advanced parts that we have in terms of technologies, but also some of the most challenging parts we have in terms of non-destructive testing. traditional NDT methods, especially if you're looking at 3D printing or additive manufactured parts, traditional typical NDT methods sometimes work, sometimes don't work, and it's a big challenge for all of us in how we kind of address AM parts. One of the trends that we've seen is certainly a push more towards CT, especially when it comes to AM parts, and I think that's part of that is because part of the advantages of doing additive manufacturing is that you can custom design each shape and each layer within the shape. So some of the walls are thinner than others, and some of the features that you have in each part, you can actually almost custom make them that you can't do from a casting or a mold process. And the problem then is being able to discern what's going on with those thinner walls that might be on the inside of the part. And then if you're doing a 2D shot on it, it kind of gets lost when you have the thicker walls on the outside. So having CT and being able to do that depth and being able to do that X, Y, and Z analysis on these AM parts, looking at these custom features that are built into these complex parts, is a huge benefit that honestly has really pushed CT to explode almost as we're seeing it. AM, we joke all the time, AM has been the biggest boon to CT that possibly could have been, just because of this, because of the advantage of being able to see inside these complex parts and being able to look at small little features within each one of these parts and being able to discern what's going on the inside versus the outside in different layers of the parts, whether you're looking at carbon or you're looking at metal printing. I could talk for hours about how CT and AM are working together, but I think you kind of get the general gist is that CT offers a phenomenal benefit of being able to do layer by layer, X, Y, and Z plane, and being able to see the inner structure very, very well of these complex parts.
Brett, I'll just ask Brett. Thank you, Rahul. That's very interesting. Brett, do you think we could have AM parts on planes if we didn't have CT? Do we need like Rahul was suggesting, we need CT to make AM happen?
So the complex the complex parts, absolutely. We have to have some of the very simple parts, different. Rahul mentioned all of the different superimposed layers. That actually makes it impossible to inspect some of those parts with 2D. It's just not possible. We can glean so much more information with CT. I've been doing CT now since 2001, 2002 in industrial, and we've never seen a boom like we have with the AM relative to CT. We're evaluating AM parts literally every day in our labs, and that's the highest volume of any type of manufacturing process parts. To his point, that was a good one about the designing aspect of it. What's interesting is, if you can get an engineer to wipe the slate clean relative to a product and just focus on performance and functionality versus how can I make it, braze it, weld it, and assemble it, and machine it, just wipe the slate clean, they can produce some amazing products. I joke with the engineers back though to say, yeah, there you go again, designing stuff for functionality instead of CT, but the reality is we can get so much more information out of a CT. And the other aspect of it is, when you think about it, we design everything today in 3D. We do 3D CAD, we do 3D FEA, we do all of our analysis and simulation work in 3D, and then we apply two-dimensional 2D acceptance criteria, which is really ridiculous because the FEA guy can plug in three-dimensional defects into a part and actually reduce the criteria for some areas and expand it in other areas based on where it is positioned within the part. You don't have that luxury often with 2D because the superimposed information doesn't allow you enough detail to understand where it is in proximity to another plane or another surface. So the CT is, hands down, absolutely bringing products to aerospace for commercial and military. They are flying commercial and military aircraft today are flying with 3D printed parts on them, metal 3D printed parts. And there's a lot of really good groups that are helping accelerate that dramatically in AM. So.
Yeah, I mean, you mentioned there that your lab is dealing with, AM parts more than ever before. I mean, to what extent is AM pushing the imaging technology in new directions and in new ways? I mean, I'm thinking specifically about, I guess, machine learning and automation to deal with these new challenges? I mean, is that something that's happening, Rahul, or is it?
So yes, everybody wants, machine learning is definitely the buzzword after AM or 3D printing. Machine learning is definitely the buzzword. Hey, we can get some algorithms from Google and do image analysis, and then it'll tell me everything I want. God, I wish it was that simple. It'd be great. I would say yes. Look, the AM is definitely pushing for further development on the CT side. We talk about how CT is a fantastic tool to be able to look at AM and 3D printed parts. There are also challenges when you're looking at 3D printed parts. Even with CT, you have, especially if you go into multi-material AM, which we're starting to see a little bit, you start getting a lot of different kind of artifacts that are coming into place. Scatter artifacts might be coming from grain boundaries that we've seen before. So there are definitely challenges that are present, and I think part of what this boon has been for CT, at least for us, has also been in terms of development of better algorithms for corrections, for scatter correction, for beam hardening corrections, for a variety of different kind of factors that we have to be able to control to get good readable CT data. It's certainly been one of the things that we keep hiring people to do is basically develop better kind of algorithms for scatter correction, for cleaner reconstructions of these parts, so you can actually glean more data from them. And of course, everybody wants more speed, right? So that's the second part. You can get like 10 different 3D printers that are going at the same time, and then they want to buy one X-ray machine or one CT machine to be able to inspect all those parts. And now you got to keep up with all this product flow, so they always want faster CT. So that's another thing that we're looking at is, higher speed kind of CT, but still being able to get good image quality to be able to do your analysis in there.
Right, is it pushing CT and in any new ways, or 2D inspection in any new ways? I mean, what in any other new ways rather? Is it?
Yeah, I think that the volume of products being printed very often they're the higher cost, larger volume, or less volume but higher cost parts. But that's going to change also as they continue to advance AM. We're talking primarily AM with metal, but AM with plastic is being used in both aerospace and medical devices today. They're even doing AM printing of pharmaceuticals. So there's a lot of applications there that just continue to expand. But one area where CT has really benefited AM is to help them accelerate the development of their new processes or even an existing process, and you have specific materials that you're modifying or you're changing the alloys. So you start mixing powders and you create new problems. So AM can really benefit from CT from the perspective of, we could do a CT scan, for example, of a part. We could do a CT scan of their build set where they have a tensile bar, for example, or a tensile coupon or material analysis coupon. And when we do that, we help them establish the correlation between whether the tensile coupon truly represents the part or not. So number one, is there a bunch of porosity in the part, and does that reflect that in the tensile coupon, so that you have a representation as far as the material properties. So CT can help them identify that, as well as just in general in the product development.
Disturbance in the internet there, I think, Brett.
Yeah.
It's either that or everyone else. He was just getting going.
Cycle to be able to do CT scan or pardon me. So Ben, did you lose me or something?
We did a little bit there. Yes, Brett. You seem to be back now, though. I don't know if you just want to finish off what you were saying. What everyone else's experience was, but I left 15 seconds, 20 seconds.
Sorry about that. Watch the guy's mouth move and don't hear anything. Yeah. Anyhow, overall, the AM process is substantially benefiting from CT throughout the whole process.
Okay. All right. Let's move away from AM, because I got the feeling we could fill a whole hour up on additive manufacturing alone. So, I mean, you mentioned a few things about automation, and do you see where do you see robotics being applied in digital radiography and CT? Rahul, is it often? I mean, do you guys work on the production side of things a little bit as well, with people working in production and manufacturing quite a lot?
Absolutely, we do a lot of this. And robotics are hell, they're also exploding along with CT for us. We see a lot more push towards using robotics. One of the biggest benefits is obviously the pricing of robots has come down, so they're actually far more affordable now than they used to be even 5 years ago. So making custom manipulators to be able to hold parts, be able to maneuver them, isn't as cost effective as actually just using a robot that's designed just to move parts. We're seeing robots and automation in general, not just robots, but automation in general, we are seeing pick up tremendously, whether it's coming for part loading and unloading into X-ray systems, so the whole conveyance system, so you need fewer operators to do it, especially when you're looking at like inline CT or inline DR type processes. The less human involvement, the better in terms of kind of optimized speed and process flow. So they're using robots to load and unload parts, do dispositioning of parts based on X-ray data, and then the robots are programmed to put it in a bad bin or a good bin and push it out to the correct conveyor. We actually use robots inside of our systems to either hold a part, especially when we're doing DR and looking at automatic defect recognition. The idea being one of the biggest challenges is repeatability of part placement. So robots offer a great deal of repeatability that they can offer, because the robot will always position the part exactly the same way every time and present it to the X-ray source and detector. So that makes that kind of automation a lot easier from an automated analysis perspective. We also have a crazy cool project that we're working on now for one of the Air Force bases that's using a couple of robots hanging off a gantry to look at F-15s and looking at fins for F-15s. And then we're actually going to be mapping out the entire room in 3D at all times to avoid collisions. So because you're using robots to hold the source and detector, they don't want to be able to collide into different components. So all that level of automation, it's amazing the what's going on with automation and robotics now.
Yeah.
Right. I mean, how are NSI using robotics and automation?
No, so you brought up some good points. There's so the mapping becomes a real struggle, especially when you start confining the space. So we do something similar where we map the inside of a cabinet, for example, if we have the robot inside, so that you don't run into something with the robot, and you don't have to worry about running into something. You basically said you don't get to move to that location. And then, so we have systems where we have two robots inside of a cabinet, where we've got the X-ray tube and the detector works its way around product, gives us a tremendous amount of mobility. But secondary to Raul's point is very often it's beneficial to just have a single robot, and you pick up the part and place it in front of the X-ray tube or on a rotational stage for CT, et cetera. So we have the systems where robots are inside manipulating parts around. Some of them reach outside the box and grab it. You could set them up. It's not uncommon to have them with conveyors feeding in, et cetera, also. And then we also have robotics where we place the robot external to the cabinet, and it picks up parts and loads it into the X-ray system. So that's not as common, but it's very helpful because you can program the door to open and shut. But what we typically do is look at it to try and reduce the door time. So whenever you have parts inside, you don't have to open and shut the door, and you can pick up multiple parts inside of the chamber. That's better, or if you have a feed through. Yeah. But everything from little small batteries all the way up to parts that weigh hundreds of pounds. It's just a matter of how big a robot you want to throw at the subject.
Okay, great. And there's probably just one or two more questions I'd like to ask. I mean, we've got quite a few coming in from the audience now, so we'll move on to some of those. But I wanted to ask about these kind of higher energy digital radiography that's been going on. I mean, how much more are we able to understand the materials and products using those sort of high energy machines? I mean, what kind of insights are we getting, and how are they useful to aerospace, the aerospace industry?
Yeah, so the cool thing about that high energy work is what a lot of people don't consider is you could have an 1/8 inch, 1/4 inch thick wall of steel, Inconel, whatever it happens to be. You can get through that with very low kV. However, let's say it's just a simple cylinder, it's a tube, and it's 5, 8, 10, whatever inches in diameter. Now you have a tangent, that outside edge that you ideally want to penetrate to be able to do CT with it. So if you're doing 2D imaging, it's relatively easy. You just penetrate the 1/4 inch times 2, or you go inside of it. But with CT, you need to try and penetrate that tangent. And so that could turn into inches of material. And that's, now you're pushing it with 450 kV. So what we do there is we bump it up to the MeV range, so the million of electron volts. So our California facility, we have a new 6 MeV system out there. And even though some of the parts that we're imaging are maybe only 1/10 of an inch to 1/8 of an inch wall thickness, but the tangents or specific regions of the part could be inches of Inconel or cobalt alloys or steel. And the MEV system works phenomenal for that. And so it's not just the materials that we're able to evaluate, these higher density materials, but also the crazy weird geometries that you evaluate with lower KVs. You get a lot more beam hardening because it's traveling through so many different variations in material thicknesses. So with additive, that's definitely the case. Rahul brought up a point about all of these different internal structures. And with additive, you need to be able to penetrate those different material thicknesses, preferably 360 degrees around. And so the high energy really helps with that. And so overall, the same type of thing, you know, with whether we do it with a manipulator or a robotic system, the fact that they're all CNC programmed. In fact, our robots, what we do is we integrated them with our motion control systems so that it's just a teach and learn versus having somebody that has to be robotic literate as far as programming. So it's just literally grab the joysticks and move things around, or the software moving around like you would with a standard manipulator.
Yep.
Okay. Well, do you want to talk to that point, or?
Yeah, sure. So, you know, one of the biggest advantages of CT or of high energy is the dynamic range that you can actually achieve. So we can do CT with low density materials and high density materials in the same setup, in the same scan, and be able to discern, say, wax from 5 inches of steel within the same kind of setup. We have labs in New York and in Connecticut up to 9 MeV that do this all day. One of the biggest areas that we've seen recently is rocket motors. So rocket motors and some of these hypersonic flight type deals where the structures are actually becoming a little bit thicker. Just to what Brett was saying, you know, especially when you have those cords on the edges, it becomes a challenge to be able to see that with 450 kV. So high energy starts coming into play. But one of the other really big advantages of high energy is flux. So with a 450 kV source, you know, your wattage that you can output from there, it's kind of limited to a certain extent. With high energy, your wattage all of a sudden explodes out. So you get a tremendous more amount of contrast that you can get within your image and the contrast detail that's captured in the image, as well as speed now. So once you move to higher energies and higher flux, you can actually start doing faster scans because you have a lot more data and a lot more contrast to be able to pick out some of those low contrast defects otherwise that might get lost with standard 450 kind of CT or DR.
Okay, right. Okay, thanks, Rahul. I mean, that's definitely an interesting area that's proven very useful for engineers in lots of different sectors. I don't know if you guys can see the Q&A that we've got coming in, but we've got a ton of questions now. So I think we should go through some of them if that's okay. I'm going to start at the top, and I guess whoever wants to grab the initiative and answer is all good to do that. It might be more who's got the better internet connection. I'm not sure, but, which Rahul might win. Let's see. But Duncan William Gibbons is asking here about advancements about in process in situ imaging during manufacturing processes for 3D printing like powder bed fusion. Are you aware of any standards being development and some of the technology that's being developed for that?
For specifically for in situ imaging of that, not the in situ for powder bed fusion, but definitely in general, there's additive documents that are being developed for both CT as well as for DR imaging. So the F42 as well as the ASTM F42 as well as the EO7 committee are both working on additive specific documents. So I think I've got one here. It's a work item associated with the additive, and I'll pick it up here real quick. So, but overall, nothing for true in situ. If they're talking about doing CT or DR while it's imaging, there's not standards being developed, to my knowledge, for CT. But there's a lot of in situ monitoring relative to, infrared, optical, and whatnot while the beds, while it's laying down the bed fusion process. There's a lot of in situ monitoring that goes on there. Our process of in situ monitoring is actually in situ of the CT scan, for example, or of the DR. So what we do is we'll take a tensile bar, we'll take an Instron system and put it within one of our CT systems, and we'll take the tensile bar, and while we're pulling it, then we'll be doing back-to-back CT scans, and we call it 4D imaging.
Okay, sure.
Sorry,
Rahul, go ahead.
Yeah, last year actually, it was like earlier this year, I was actually invited to this imaging panel at Cornell. So present there were some Air Force people, Army Research Labs, some of these kind of like forefront thinkers for kind of powder bed fusion. And a lot of, right now, there's no necessarily standards. There is more and more X-ray being used and actually looking at high-speed X-ray to be able to look at the melt pool, to be able to look at as the part is kind of being formed, which part is being hardened, and being able to measure different kind of splatter and being able to kind of look at various forms of measurement. But there's no necessarily standards right now. I think, as Brett was mentioning, the ASTM committees are certainly meeting to generate standards for AM in general. But right now, I would say, looking at powder bed fusion in situ is more R&D than it is production that can actually be standardized.
Yeah. So the one AM for CT, the work item is 71550 is an ASTM work item. If you looked at the ASTM.org website. So.
Okay, cool. All right. Okay, so Thomas, pardon me, Thomas, if I get your surname wrong, but Thomas Nusel has asked a couple of questions. One of them is quite commercial, but I'll start to do with justifying the purchase. But I'll ask the second, more technical question first. Is there a size and/or geometry limitation for DR and CT when inspecting carbon fiber reinforced polymer parts?
If you can fit it into the cabinet, you can image it and you can inspect it. So, especially if we use LDAs, if we're doing DR and CT when using a linear diode array, we have LDAs that we've used that are 6 feet long or even longer. It takes a lot longer to be able to do that, process all that data. We've done scans, or our partners have done scans of entire Tesla Model X's or entire vehicles. So I wouldn't say that there's a limitation. The more the limitation is how long you got to be able to scan it, and do you have computers powerful enough to kind of process all that data and crunch it all. But yeah, we've done some rather long and big parts already. Yeah,
that becomes a data issue definitely when you're dealing with those large parts. There's also the occasional situation where if it's just a flat plate of material and you're trying to scan that, and if you're looking for voids, that's really pretty simple in 2D very often, or local CT scanning. We also have what we call a mosaics setup, where we can take our detector and stitch it, move it around and stitch it to be able to create a virtual detector that it's number of feet in both directions. But to Raul's point, depending on the spatial resolution or the resolution of that detector, the number of pixels, the data size gets massive when it comes to CT. So then you throw bigger hardware at it relative to the computer processing powers. But the other part of the equation, though, is if it's, let's say it's 5 feet of just a flat plate composite and they're looking for voids, that's fine. If they're looking for delaminations, we always look at, what's the best tool for the application? And the best tool in that case very often is ultrasonics, unless they need a better spatial resolution. And so we try to help our customers point to the optimal technology. There's some applications where laminography or tomosynthesis lends itself well to some of those big flat surfaces also. Okay,
and justifying the it says here high investment for DR and CT equipment to management. What do you how do you justify?
It's a great question. I think the key is always to focus on your total cost of ownership, right? So yes, your upfront cost or your upfront capital cost is going to be high. And if you have a person that's just looking at immediately, all right, this is what's coming out of my budget, what am I getting out of it? It's the wrong way to look at it. Film is always going to be cheaper from that perspective. But if you start looking at what value do I get out of this system? How is it going to save me money, 3 years down the road? What do I look at? So if I'm looking at a CT system, hell, I can start CTing parts before I even release them to production, right? So during the development process, and I can save months of development time if I start looking at parts and scanning them in different stages and seeing what's happening. I can do fluid analysis. I can do FEA analysis based on CT data rather than actually destroying real parts and being able to cut them out and then doing all that. So it can save months and months, especially as you're taking parts to go into production, which has phenomenal amounts of capital savings at that point, and commercial implications if you're first to market and if you get something out there. So I think the way to justify it is not just look at what the actual price of the equipment is, but what is the value that equipment is bringing to you, not just now and what it can do for your process steps, but 3 years, 5 years, 10 years down the road, where you don't really have to replace too many things. And if you look at it over a 5-year horizon, the amount of film that you would have bought is probably more than justified by a DR system or a CT system, but you get so much more out of it.
Yeah. Yeah, that time to market is huge because what you can learn about the process without cross-sectioning as well as finding those failure points prior to just release. To find them early, that's absolutely huge. And it's one of those things that's hard to put dollar value on. But we've had systems where somebody just fought tooth and nail to get the budget within a company and got a whole bunch of groups together and whatnot. And then literally this happened where I got a call 3 months later and he said, we just paid for the system. So they had like a 2-3 year ROI that they put together. He said, we just paid for the system. And how they paid for it, they've caught a failure that would have been catastrophic for them before it went out into the field. And they had a whole bunch of product ready to ship and they caught it there and they were able to sort it and meet their customer needs. Had that not been there, had they just relied on their ultrasonics, they were not able to detect it. So yeah, it's one of those cost avoidance sometimes.
Yep. And reputation damage. I mean, God, just as Chipotle is still recovering from that E. coli disaster. If you have better quality control and you catch stuff before it goes out to consumers and market, you get to protect your brand image. You can't build your brand image back once it gets hurt.
Yeah. Great. Okay. I'd like to ask this question from Peter Friedolf, but he's asking here, how far away are AI ADR for welds? I'm guessing he means artificial intelligence, automated defect recognition, to create. How are you able to create a detection mode for defects that are very close in pixel values to the base material? Anyone want to take that one?
Yeah, I think that so the Metals Affordability Initiative, the MAI group, had worked on a document for how we do assisted defect recognition. And from that, we generated a new, it's 60469. So it's an ASTM work item. In fact, I believe it was just passed in ballot. But that's a guide for the qualification and quality control of computer-assisted evaluation for DR test data. That's going to be really instrumental in the industry for how to help set up assisted defect recognition, whether they're using AI or not. But there's a lot of AI work that's going on specifically to help with automatic defect recognition or assisted defect recognition, and basically teaching it, hey, here's what it looks like. But the question more lies in, what do we have as far as a quantity of pixels and a gray value or pixel intensity value that represents the defect compared to the surrounding material? And that most of the time is material or equipment selection and technique. What commonly is missed in the industry is people doing things to further improve on or reduce the impact, negative impact of scatter radiation. Scatter radiation has negative impact on contrast sensitivity. So very often we can just drive the technique differently for optimization of that variation between the two, the defect or discontinuity in the surrounding material, because it's you have to have that so that the computer can pick it up. And otherwise you're creating a whole bunch of false positives or false indications of defects by the automatic or assisted defect recognition, and then that slows down the whole process, and it slows down the confidence.
Yeah, I agree. Technique development is absolutely the key. Whether you're using copper filter or something in front of the beam to kind of beam hardening and get rid of some of the low voltage, low kV photons to be able to get better kind of clarity on the imaging side, whether you're looking at shuttering or even masking on the detector side to be able to reduce some of the effects of scatter. And if you're using it on the DR side, maybe you shoot it from a different angle or a couple of different angles. That's one of the things that we also find in common is people only think about it in terms of film sometimes. And with DR, with robots, you can shoot it from almost any angle that you want. And you'll be able to kind of see that area a little bit more clearly. Low density defects are always a challenge, especially when it comes to ADR. You can always set your sensitivity on ADR really, really high, but then you're going to have so many false negatives or false failures that it becomes useless as a tool, because you're just going to have to wade through all of that. So yeah, that's part of what we do is we help customers come up with better techniques that might work. We say, hey, send us a part, we'll shoot it, we'll see if what we can see on our side, what you can see on your side, and show you how maybe to shoot it better.
Okay. Yeah, I think one thing to expand on that just briefly was also there's a lot of these products where they've kind of got it ingrained that we have to do 2D imaging and then ADR with that. But very commonly, if CT can be done on the part, you can very often do CT just as fast as the DR. And you can, if it warrants, if the physical geometry and whatnot, you can get the energy through it. And you can glean much better contrast sensitivity with the CT. So we've replaced a lot of DR applications with CT specifically for assisted defect recognition.
Right, okay. And this kind of feels related, but Daniel Hecht would like to know what are the typical effects from voids, cracks, WRT to scatter noise. Can you adjust some of it? Does that make sense to you guys?
You can, look, yeah, I think he's asking for internal defects within parts that might be causing scatter artifacts to appear within CT scans. Hey, that's somehow how you learn that there's a defect going on if you start seeing artifacts. And yes, there's physics-based modeling where you can actually model what your scatter pattern should be based upon the geometry of the part. And if you're getting a different scatter pattern, or if you're getting kind of different image quality than what you'd be able to model out, that's usually an indication that something might be going on in there. You can certainly try different energies. Are a way to kind of help reduce some of that scatter. Typically, scatter is either caused by complex geometries or kind of low photon power, essentially. So if you start increasing your energy and increasing your wattage, you might start seeing some of that scatter to go away. And then there's other things that you can play with, but it depends part to part. There's no real clear-cut answer, I would say. Right?
Yeah, so it's the the scatter from a contrast sensitivity standpoint becomes really important. And so often, when some of the things that people don't consider, because especially for people that are coming from film, you always put your part on the film and then you shoot it. Well, you have product scatter that always lands directly behind the shadow of the part on the piece of film. And so, for example, if somebody's shooting at 40 inches and they have their part at 2x magnification, now they have 20 inches that the scatter has to be able to translate off of the detector or from behind the shadow of that part at 2x magnification. You double that focal distance to 80 inches, just for example's sake. Now that, let's say, 1 or 2 degrees of scatter angle coming off the part travels further away from the shadow of the part. So there's things like that that we can do in technique that help product-related scatter substantially.
Okay, great. I wanted to ask these questions from Gregory Bell quickly. First was something that something that you mentioned earlier on that I wasn't familiar with as well, and that's flux. Could you explain what that is first, please?
Sure. So flux is wattage, right? So wattage is kV and MA. You multiply them. That's how many kind of watts you're generating from the X-ray source. And what we term is flux is basically is how many watts are coming out. And for thicker parts or for parts where you are trying to get faster imaging, the more wattage or the more flux you can generate, the better contrast resolution you're going to be able to pick up. So it's essentially saying that you're increasing your MA, if you were to say that at a certain kV. But when you look at high energy, you don't really talk about MA. You talk about flux that's coming out of a high energy source. So it's equivalent to wattage.
Okay, and Brett, he's asking here about machine vision as well, being used to identify quickly irregularities in CT scans in medical applications. I think I've heard of that happening in engineering and materials. Is that something that NSY are looking at?
Yeah, absolutely, as well as in the medical arena. So, for example, we've actually done clinical studies with different clinics as well as hospitals and research labs, where we would, for example, take a heart that's been removed from, let's say, a lamb, and it has a heart valve in there, and we're looking for calcification over time. And they can, obviously, you can only do that once. You can't put it back in and get the thing running around and see what it builds up. But they can compare that over time with different drugs and things like that and see what the indications are relative to calcification buildup over time on the heart. And that they use an AI type of approach to evaluate the differences, as well as in the medical industry, they're using AI to help learn and identify different tumors and things like that. And so from assisted defect recognition or automatic defect recognition in software, you can take those programs and add AI to it to help it learn. Additionally, we can do it in reconstruction algorithms for, Rahul mentioned beam hardening and things like that. But we can also apply it to, let's say we give it a CAD drawing and it says, here's the known, here's what this part looks like. And we can help use AI to further improve on the image quality, make things a little more crisp, etc. So let it learn, basically. DR, 2D imaging, that's done a fair amount in the industry where people, a lot of it's still experimental, but I think some of it may have rolled out from some of the primes in production, that they've done a lot of experimental work at least.
Yeah, and we're actually, we have 4 different R&D projects ongoing right now for looking at machine vision and looking at AI for aerospace or defense work. 3 of them are SBIR initiatives. These are small business initiatives from the federal government here in the U.S., where they actually sponsor some of this research or fund some of this research to be able to do it. And so they down select some companies that can do it. So we're on 3 of those right now, looking at different AI and machine vision algorithms, looking at munitions, looking at base gap measurement in munitions, looking at propellant measurement in rocket motors, and looking at some AM parts as well. And as Brett mentioned, there's a whole bunch of stuff that can be done looking at taking out existing 3D CAD models and kind of doing actual versus nominal comparison with CT data, and being able to use that data and to be able to say what's going on in the part. You can do, and some of the CT software now has gotten phenomenally powerful, where you can do, fluid dynamics and be able to look at how, if you were to actually use this part, how would things flow through it, and be able to analyze that, which is, and then build out a tool from there. So.
Okay, great. Okay, so I think we've got time probably just for a couple more. I realise there's some questions that we haven't got through, and I'm really sorry to those people. Perhaps we can address them afterwards. But I'd really like to ask this question from Frank Miranda about AM parts and planar defects. He says that the challenge has been the detection of planar defects, the lack of fusion between the layers with AM parts. Concurrent CT reconstruction software find planar defects in AM parts. Anyone want to take that?
Yeah, I think that, so we actually do a lot of that work, and we, in fact, just this week, yesterday I had a conversation with a customer where what we did is we set up a representative quality indicator with planar defects in it. So we generate planar defects that would be representative of what that given process would generate, whether it's a powder metal bed system, or whether it's plasma deposition, for example, which is more like a weld bead going down. Either one of those processes has specific parameters that are more likely to generate these planar, it's kind of like a lack of fusion type of defects, or an unfused powder. And so what we do is we put RQIs in the system to make sure that we can detect that to whatever the minimum planar physical size is in, let's say, elevation. And then we prove out the qualification of the technique that way. And sometimes they actually just print that if possible. It's not always easy to do. It is with a powder bed, but not with the deposition systems. And the one thing that you have to consider in this CT technique is the build direction. Yep. So if they're building it vertically, then you want to take that into account in how you set up your technique. We have vortex imaging, for example, that allows us to do helical cone beam CT. And so you're always aligning the beam with those flats where the highest probability of planar defects would occur.
Okay, right. Okay, in fact, I've been telling, well, Rahul, do you have anything to add to that? I've been told that's the last question. I'm not quite sure who's telling me that, the internet overlord somewhere. But do you have anything to talk to from that on that point, or about planar defects? Or?
I think Brett covered a lot of it. Having knowledge about the way that the part is formed is key in order to catch those defects. To be able to scan it in the right geometry based upon whether it's being built horizontally or vertically or however is key to. So understanding the build process is key to be able to catch those defects.
Yeah.
Great. Okay. Well, I mean, we covered a lot of ground there. I hope that everybody who attended found it interesting and educational. I certainly found it both of those things, and I'd like to thank you, Rahul, and you, Brett, for participating and sponsoring and making it happen. It's the first time we've done this on aerospace testing, and it's.
He lasted to the last bit.
and then we lose him.
Yeah.
Ben, we lost you temporarily. Oh, lost him completely. All right, well, take care, everybody. If